Hello, welcome to debunking particle wave duality. Physicists believe that light behaves both as a wave and as a particle. They have named this particle of light the photon. I'll show that physicists have inappropriately ascribed the corpuscular nature of their instruments to light. And I'm going to show that for both the image intensifier version of the experiment as well as the photographic version of the experiment. I'm going to show you using Nyquist theorem that it's not possible to prove the particular nature of light using normal matter. So first, let's introduce the experiment. Okay, what we have here is the double slit experiment, and we have parallel wavefronts impacting two slits, and what happens is you have what's called diffraction occurring, where the waves swirl out and then they hit the barrier on the side here. Areas where the crests overlap, you're going to get a bright area where the crest falls in between, the peak to trough, you're going to get a dark spot. And this is what we call a fringe pattern. Now, there's a great site called Veritasium, and the guy's able to show these bright and dark areas using a couple of paddles on a pond. It's really, really good. You should go check that video out. What physicists have done is they've taken this experiment where they put a laser beam into a double slit and then into an image intensifier, into a CCD camera. Now, it might be hard to see from up there, probably is hard to see. I don't think my printer has a resolution, but over here, there's only about a dozen green points of light. And what they've done is that's for one frame, so they take 200 frames, 1,000 frames, 5,000 frames, 20,000 frames, and up to 500,000 frames, and you can start seeing the double slit pattern, what we call the double slit fringe pattern. Okay, but the problem with this experiment isn't that you get the double fringe pattern. The problem is they put in attenuators in here. They're intentionally dumbing down the light so that they can come up and show you these couple of points over here and say, aha, these are photons. And I'm going to show you that is completely wrong. Okay, there is another variation of the experiment where instead of using a photomultiplier or image intensifier, they just put photographic film here. And with a very, very short exposure time and attenuators, they get a couple of points hit. And then as they allow the film to integrate, the longer you leave film going, the more it integrates. They end up getting back to a solid double fringe pattern. I'm going to show you that this particulate nature of both of these means of detection are a property of the detection means and cannot be attributed to photons. And I'm going to do that with the Distinti palm tree wave detector. Assume you have a tropical beach with palm trees lining the beach. And then if a high enough wave comes in, a strong enough, powerful enough wave, you're going to clear cut all these palm trees away, and then you have your detection that a wave occurred. But if we do what the physicists do, and we put an attenuator down so that the wave coming in is like much, 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 much smaller, so that any given wave can't knock over a tree, well, eventually, after maybe thousands or even millions of smaller waves coming in, eventually you're going to have enough beach erosion that a tree that is more susceptible, maybe an older tree or a sick tree or a tree that has an infestation, maybe a tree that gets with a little bit of wind, kind of like noise, one tree might fall due to wave action. But again, that's going to take millions or thousands. This is like exposure. If you have one big bright wave, you knock them all out. If you have very small waves, you have to take a much longer exposure before your wave detector can detect that you have waves coming in. The problem here is that light waves coming in have done such a gradual, slow work, you've only lost one tree. And it's very simple to see how somebody could misidentify that, oh, yeah, well, maybe water is made of buckets of water, and the buckets of water, it's particulate, it's packetized. No, you cannot make that assumption for just one tree falling down. Here is that they have a CCD camera. Okay, a CCD camera going into an image intensifier. Okay, so a CCD camera is a normal movie camera, like what I'm using to videotape this right now, or video this right now. A CCD camera has, let's say, a 60 cycle frame rate, which means its exposure time is a 60th of a second or less. So if we take a single frame of the CCD camera, that's 1/60th of a second. Let's assume they're using red light, which has a very, very long wavelength, and that's 700 nanometers. And speed of light, we'll just round it to 3 times 10 to the 8 meters per second. So the length of light being integrated by this system for any given frame is 5 million meters of light. 5 million meters. The number of wavelengths for this is 7 trillion wavelengths. So you're saying that we have 7 trillion wavelengths hitting our detector, that we only detect 12 photons? Really? Really? That's insane. But you know what? Let's do this. Let's go and see what one of these image intensifiers look like. Oh, well, okay. They sort of gate these things with a 100 picosecond gate. Okay, that doesn't really help us, because even though you're gating it with 100 picoseconds, you're still integrating over the 60 hertz frame rate. But even then, with a 100 picosecond gate, you still have to integrate 4,000 wavefronts. 4,000 wavefronts. Okay, and here's the other problem with this, is here you have this plate. This is your photocathode, which has got electrons that are being energized by light, and then what you're going to do is put a very, very high voltage, negative voltage on this side, which is going to cause them to say, hey, I don't want to be here. So you're almost helping them jump off. And then what happens, they're going to jump into these microchannel plate, where they're going to bounce around, causing other electrons to bounce out until you get a flood of electrons hitting the phosphor screen, which is where you get the green dot that's seen by the the CCD camera. Okay, this, my friends, is a high gain amplifier. And any engineer that works with high gain amplifier realize they have a very large noise figure, because of this high amplification status. And so what you really have is, because they've attenuated the light down, so you might have this detection level, that this is the level needed of energy to push an electron from the cathode down the microchannel plate. Now, the noise in and of itself might be down low enough because they probably have cryogenically cooled this thing, so it's a lot less noisier, but you're still going to have noise. Okay, then this actually might be the intensity of light hitting the plate. Okay, but over here, you've got a noise bump that's just at the point of knocking an electron out. And even though that's going to be in the null, there's still some light there. So you're going to get a detection. You're going to get a pixel in the middle where you should have a null. And over here, where you have a little bit more light coming in, and you're going to have like 4,000 wavefronts, there are odds that you're going to push a piece of noise up into the detection range, means you're also going to get a speck of light here. Okay, you're going to have noise. And what they have is they have noise riding on top of their signal. And all their signal is going to do is push the noise up into the detection range and make it look like they have a particulate nature, a particulate detection. But the key here for us is they should also have noise coming up where they should have nulls. And we can see that. Oh, it's harder to see on this one. But if you go and look, I'll put the link down for it so you can look at it in closer detail. Look at the 200 frames, and you'll see down in the nulls, you'll see there's spots down in the nulls in between where the what do you call it, the wavefronts are peaking. That is clearly an indicator of noise. This, my friends, is the one done with film. Film doesn't have a noise problem, so you can see down in the nulls it's complete black from top to bottom. Complete black from top to bottom. Except possibly for this guy here, which an error in the photographic emulsion. Every place where there's supposed to be a null, it's complete black. No noise. If you look at the one from the photo intensifier, you see noise. And in this one here, at the 20,000 frame, it's hard to see from the camera, but there's a sheen of noise over a cast of noise over the entire frame. Okay, this is certainly not, this area over here, this is certainly what engineers would expect from noise. Okay, and if you look at the one, you compare, when you go there on your own, compare the 20,000 frame version to the 500,000 frame version. You'll see over here where it's supposed to be absolutely dark, there should be no pixels being produced over here. But here you're going to see a definite noise floor. Okay, and the other thing is that this is how we engineers integrate to get rid of signal to noise. Because if we got noise over the entire picture, which we have here definitely, by integrating thousands and thousands and thousands of frames, the intensity where there is coherent signal increases at a faster rate where there's incoherent noise. And that's how we pull a signal out of the noise. So this is definitely a noisy frame. This is not the indicator of pixels. Here's another example using a television set. Ironically, a television set is almost the exact same thing as a photo multiplier tube, except the parts are rearranged a little differently. Again, it's a high gain amplifier. And it's hard to see from this bad print, but over here there are little specks of noise that are just popping through the detection range. There's little pixels here and here that are hot, because this is where the transmitting station is sending no signal, and the noise floor is just at the detection range. And so the peaks of the noise are popping through. Over here, where the transmitting station transmits just a little bit of energy, it pushes all the noise out of the noise floor. You can see all the noise riding on top of the transmitted signal. Okay, this is an example how signals can push noise up above the detection range. Comparing to film, again, you can probably see from the camera that this null isn't perfectly dark in here, that there is spots, whereas the nulls on the film are perfectly dark. That's because film is a different detection medium than the photomultiplier. Okay, the reason for this is film is intentionally manufactured with varying different grain sizes, widely dynamic varying grain sizes, from humongous large grains to almost tiny microscopic grains you can't see. This intentional varying of the grain sizes gives film an incredible dynamic range so amateurs can take decent pictures. And what's interesting is that the larger the grain is, the more susceptible the grain is to very low light levels. In other words, it doesn't take a lot of wavefronts to turn this grain on, as opposed to a tiny grain takes a heck of a lot more wavefronts to accumulate enough energy to turn that pixel on, or that grain on. Okay, and that's why you get a much more grainy appearance with film in low light. If you ever took a movie that was filmed in the 1940s and 50s, get it on a high definition medium like a 4K DVD, and put it on a high definition television set, go look up close and look off into the corners where it's dark, and you're going to see all kinds of things that look like ants running around. That's the grain of the film, and it's grainier at low levels because of this intentional structure of the film that was designed to give film a great dynamic range. Now, what do I mean by dynamic range? Well, if they made all the film grain in the film exactly the same size, this is what photography would look like. So at the same film grain size, there is one level of light that will either turn a grain on or not turn a grain on. And this is a photograph of Audrey Hepburn, a high contrast photograph. And you can see wherever it's black, it's completely black. Wherever it's white, it's completely white. But there's a lot of missing information, a lot of missing tone. The right side of her face is missing, her right arm's missing, her left ear is incomplete. Don't mind these little pink blotches, that's my printer on the fritz. Okay, and so this is a case where, now you can actually do this with, in post-processing with a computer using digital, and all you have to do is say, if the light is below this level, I want black. If the light's above this level, I want white. And if you keep trying to change the light level, you can get you can actually make this all black or all white. And that's why this kind of high contrast film is very difficult for amateurs to use, because it requires the right light level. And it requires sometimes a lot of trial and error for a photographer to get the hang of using high contrast film like this. This next example, again, Audrey Hepburn, is still high contrast, but with a little bit more grain variance. Okay, you still have saturated white areas and saturated black areas, but now you have halftones. And you can see if you blow up this area, which is over here, you can see it's very granular. I'm sorry, I'm trying to blow up a JPEG. I wish I could get the actual medium and actually blow it up for you, but you can see how it's kind of grainy in here. That granularity is not photons. That's the intentional properties of film by the manufacturers to give the film a little bit more dynamic range. And if we go to normal film, this is really bad. This is actually nice. This is better in real life than it is on the printed page, I'm sorry. But this is a little more brighter here. But this shows when you increase the grain diversity as well, you get much better halftones, much better saturation. And this is the kind of film that they would put in old Instamatic cameras in the 60s, because you didn't need a fancy light meter in your camera to take good pictures in a lot of varying light conditions. So this kind of dynamic range is intentionally caused by the people that make the film. And that gives film granularity, high granularity under low light conditions. And there is a resolving, this is from 1963. This journal is out of publication because nobody really deals with film anymore, but they showed 9 different types of photographic films under different conditions to show how different types of emulsions react to different light conditions. Not photons, this is the reaction and the behavior of the emulsion. This isn't photons. This is a picture of, and this actually came out better in the print, of a child's face. Here's a, you know, blown up so much that you can actually see it looks like a whole bunch of speckles that are making, this is the grain of the film. This isn't photons. These very bright, big grains that are over here, because those are very large grains and they're more susceptible to low light conditions. That's why they're brighter. Okay, and that's how they get the shading of the film, so you can get that good dynamic range. And you can see how much it looks like one of their double slit patterns over here that are also under low light conditions. So, the recap part 1 and 2. Part 1, we're talking about the image intensifier. Part 2, we're talking about the film media. Physicists have just attributed to light the corpuscular, granular, noisy nature of their instruments. In order to prove the particulate nature of something, you need something with at least a granularity twice as small as the thing you're trying to prove is granular. For example, if you want to quantify audio, that when audio range is 20 to 20,000 hertz, you must sample at 40,000 hertz at a minimum to be able to reproduce the sound with enough quality. And let me give you an example using shoe size. Suppose your ruler for measuring feet only had, you know, 1 foot and a 2 foot index, and that's all you had. That's the granularity of your measuring instrument. You either get a measurement that's 0, 1 foot, or 2 foot from your measuring instrument, nothing else. How good do you think it would be for you to put shoes for a kid or an adult? It would be horrible. You would go out of business being a shoe salesman. But if you had a measuring instrument that had much more granularity, you could get shoes much closer and be a much more successful shoe salesman. Okay, and that shows that your measuring instrument has to have the granularity smaller than what you're trying to measure. And if you look at what we've done in the past, we've used X-rays. X-rays have a wavelength 100 times smaller than visible light, and X-rays allow us to make images to see into DNA and other crystal structures. This is the X that you see when you do X-ray crystallography on DNA. That's where the movie The X-Men get their X from. Okay, so in other words, what this means is that the resolution of light is actually small enough for us to make some sense about what the structure of crystals are, which means that light has to be smaller than crystal structures. But it goes beyond that, because gamma rays have resolution down to atomic nuclei and probably beyond that. Okay, so the wavelength resolution of light is far beyond, below the size of any corpuscular matter that we have any knowledge of. And therefore, if the photon did exist, we would need some kind of matter that has at least 1/2 size of a photon. For example, if we take our beach detector, and everywhere where trees fell, they fell in pairs. Well, we could say, hey, gee, somebody drove a tank up on the beach. You know, we can say that whatever is knocking down these trees is at least twice the big of the granularity of the trees, at least. Okay, but if it's just one tree, we can't make any conclusion from that. Because the effect could be, like I said, a very, very low effect that takes a long time to integrate and takes just one more sensitive piece out, because these trees aren't uniform. One tree might be more susceptible than the rest. You don't know. But, you know, with our palm tree detector, if we had some waves coming ashore, as long as the size of the waves are much bigger than the granularity of our palm trees, we can definitely say where the trees are cleared away after, you know, millions of wave fronts finally clear them away. But here, where you have the nulls, the trees are still standing. Well, the size of the waves that we're measuring are much bigger than the granularity of our detector. Okay, that's Nyquist for you, baby. So, as long as your granularity of your thing you're trying to measure is at least twice as big as the granularity of your detector, then you can make serious conclusions about what you're seeing. Losing 1 pixel tells you absolutely nothing. Okay, trees knocked over individually only prove that your detector is corpuscular. It tells you very little about the phenomenon you're measuring. Because like I said, it could be lots of waves hitting this, and eventually the weakest trees fall away. But my hats are off to engineers, because they're selling physicists photodetectors configured to detect individual photons, which is complete nonsense, because I've shown you before it takes thousands or millions of waves combined with noise to finally get one of those electrons to bounce off from one of these, from a photomultiplier, from a single photon of avalanche diode, superconducting nanowire single photon detectors. That's all bullshit. There are no way that you can prove you are detecting single photons, and more likely you're ascribing the globular, particularly the corpuscular nature of the matter you are using to measure light. That's what you are using to measure light with. And all you're doing is measuring the corpuscular nature of your medium, because light is much smaller than anything, any kind of matter you can put in the way to measure it. And so it's very unlikely you're measuring single photons. It's probably not the case you're measuring single photons. So here's some misquotes by P.T. Barnum. A physicist and his grant money are soon parted because these engineers are selling you stuff under a false pretense that you're actually measuring photons. You're not measuring photons. Again, there is no matter small enough that allow you to measure individual photons. And I've said before, you got to measure multiple waves. 4,000 to 7 trillion waves are what's needed to knock an electron, depending on the intensity. And there's a physicist born every minute. Again, physicists have improperly attributed the corpuscular nature of their light detection devices to light. And let me run this by you. We know this to be true, that light of higher frequency has a higher ability to knock electrons out of orbit and give you a green dot on a detector. It can be done with a shorter exposure time because higher frequency electromagnetic radiation has more waves per unit length. And that's where it has the added ability, it has more chances to bang at that electron and knock it out on you. And therefore, it's not a case of a higher energy photon, it's a case that you have a wave train that's much more densely packed and has a higher chance of knocking something out. So this is more evidence of multi-wave action, like I've been saying from the beginning. It takes multiple waves to knock an electron out. And finally, because electromagnetic radiation has fine enough structure to enable us to discern the larger corpuscular nature of matter, or structure of matter, then it is not possible to use matter to discern the structure of light, other than if it's waves. You can't tell what light's made of. You can tell light comes in waves. But so if light were, in fact, photons, then the photon, that's hard to see. We can imagine if you're trying to, you can't see, let's say you can't see the basketball. Okay, let's say basketball represents matter. But if you had very small particles of light, let's say light were made of photons, well, you could take that light and bounce it off the basketball and eventually shoot enough pieces of ping pong balls around, and even though you couldn't see the basketball itself, you would be able to see where the ping pong balls bounce off of and be able to take a good measurement of what you're trying to discern. And that's what we do pretty much with X-ray crystallography. But again, I don't believe in photons. But you can't do it the other way. You can't use matter to infer photons, because there's no way you could take the corpuscular nature of matter and then try to discern something that's much, much smaller than it. No way. And this is why it takes lots and lots and lots of wavelengths of light to knock electrons out, because light, the structure of light is very, very, very small. So you're not looking at photons. You have not proven photons. Okay, we can only make conclusions about the structures that are larger than the resolution of the detection devices. In other words, you can't attribute anything to an individual pixel that is turned. All you can look at is say, oh yeah, through all this noise, I do see that we have periods of absence of pixels and periods of waves coming through, and that we do have an interference pattern. That's all you can do, because at least these structures are larger than the resolution of your detection means. It's Nyquist, baby. And this is a really good quote from, I put the photon as humbug. This is just his quote about science. P.T. Barnum again. I see photons. This is what this reminded me of. The little girl from Poltergeist that goes up to the TV and says, they're here. And I say, no, it's just noise. So the final conclusion. The attenuated double slit experiment does not show the existence of particles comprising light. It just shows the behavior of the corpuscular nature of the detection means at low end of its dynamic range. By attenuating the light, physicists are just destroying the signal-to-noise ratio of their experimental apparatus and attributing this granular noise behavior to the properties of light. I have lost all faith in physicists. Now, a little background info. I was going to write this as a paper and submit it to a journal, but I got to the point where, you know, it's going to get in the front door of the journal and somebody's going to say, duh, you know, if this were true, somebody would have said something by now. And it's just going to be, you know, I just don't want to deal with it. I'd rather go on with Ethereal Mechanics. It doesn't help me to help educate physicists, okay? And this all started because I was working on, there's some issue I'm missing with magnetism, and I realized I need to go back and study what the reference frame of magnetism was, and I started doing analysis on the Michelson-Morley, and I realized, oh my God, physicists had missed a whole bunch of things in the Michelson-Morley experiment, things based on the nature of light that they're totally clueless about. Okay, and if you want to see that work, there's a free paper at my Patreon site called Transvariance. It's paper version 1.2. Look for keyword transvariance. The transvariance paper replaces special relativity. The new paper on gravity, which I'm starting now, is going to replace general relativity. And please get the word out about this experiment. Go to all the places where they start honking about the particle wave duality and the photon, and just start saying, no, you guys got to see this video by this crazy Distinti engineer guy. Okay, and please support me on Patreon. Here's what I'm going to do. Okay, I need more Patreon. When we get to 100 Patreon members, then I'm going to do a video about quantum entanglement. Another piece of bullshit. Oh my God, you wouldn't believe it if you really understood what was going on. But I'm not going to bother because I don't really need to prove physicists wrong, okay? But if people are interested, please get me some Patreon support. When I get to 100 Patreon subscribers, then I will do the paper on quantum entanglement. It's going to be just as fun as this one. I forgot to remember what I was supposed to remember here. The next, we're going to show that the circularly polarized light is in fact humbug. That video might be out this weekend. It'll most definitely be out next weekend. And for patrons only, I'm going to show a video of how polarizers really work. And there should be some really interesting applications in there. No, it's just noise. Thank you very much.